In this question, we're asked to find the volumetric flow rate between these two tanks in this system. So you can see from the diagram that tank A is open to the atmosphere, and also tank B is also open to the atmosphere. There's a height difference of 20 meters between the water surface level in tank A and in tank B. We're given the dimensions of the pipe, its diameter and its length. You can see there's a pump and a valve in this pipe network. And we're told that for turbulent flow, the pipe friction factor is 0.025. I'm also given the pump characteristic curve. But just notice here that this is HP, so this is the head of the pump. So in other words, this is in meters, not pascals, so we just need to be aware of that later on. We're told that the loss coefficient through the valve is given by this general formula, and the loss coefficient for the valve is 10 when it's fully open. Now, ignoring all other minor losses, we need to calculate the volumetric flow rate when the valve is wide open, and we're given the viscosity of water as well. So to solve this, we start with Bernoulli's, where if you remember, the static pressure plus dynamic pressure plus dynamic pressure at point 1 is equal to the same at point 2. We have our pressure loss term between the two, and also the pressure rise due to the pump. Now, as we've done in previous examples, we're not told where to take point 1 or point 2, but a good place to do that is to take point 1 as the surface level in the first tank, or tank A, and point 2 is the water surface level in tank B, because we know information at these points. So we can simplify this by making some assumptions. So we know that by assuming that the area of the tank is very large compared to the area of the pipe, therefore the velocity in the pipe is very large compared to the velocity in the tank, and therefore we can say that the velocity in the tank is negligible, so the velocity in tank A, or C1, is equal to 0, and C2 is also equal to 0. Because we've chosen to take the surface points in each tank, we know the static pressure at these points is equal to the atmospheric pressure, so therefore P1 and P2 will cancel, C1 is equal to 0, so that term disappears, C2 is equal to 0 and disappears, and by taking the height of the water in tank A as our datum, we can also set Z1 equal to 0, and we set Z2 to be 20 meters. So this is what it simplifies down to. So the pressure rise, or the pressure required by the pump, is equal to the change in potential, going up 20 meters, plus the losses through the pipe network. So we can go ahead and work these out. So recalling that the generic formula for the pressure loss for a pipe system is the frictional losses plus the sum of the minor losses, all times by density and the velocity in the pipe squared over 2. Now we need to do this for each section of pipe, remembering where a section of pipe is of constant diameter or constant material, and we only have one section of pipe in this example. So we substitute the values in. We know what the density is in gravity. We know what Z2 is, it's 20 meters. We're told the friction factor of the pipe, assuming it's fully turbulent, and we know the dimensions of the pipe, so we can substitute that in. Now, in terms of summing the minor losses, in fact, we have 3 minor losses here. We have the entry loss into the pipe, the valve, and the exit loss from the pipe. However, we were told in the question that we were to ignore minor losses except for the valve. That was the only one that we were to include, so that's why we've only got one here, and the value of that loss coefficient was equal to 10, all times by the density of water divided by 2, and we don't know what the velocity of the water is. This is what we're trying to find out. So when we work that out, we end up with the pump pressure being a function of the velocity in the pipe squared. Now we're trying to find the volumetric flow rate, so we're going to substitute in the velocity for the volumetric flow rate. So c squared is equal to volumetric flow rate squared divided by the area squared. And we also know that the area is equal to pi d squared over 4. So do it yourself. If you put in the area for pi d squared over 4, then when you rearrange it, you should end up with this, because obviously you're squaring the area. So just prove to yourself that you can get to that solution here. Now we substitute that in for c squared into our formula. So now we have it as a function of volumetric flow rate, the pressure rise from the pump in terms of volumetric flow rate. And this is what we call our pipe characteristic curve. Now remember, to find the operating point of the pump, it's that operating point is where the pipe characteristic curve and the pump characteristic curve intersect. We've got our pipe characteristic curve, but just note here, the units of this equation is in pascals. And we do have the pump characteristic curve, we were given that in the question. But as I said at the beginning, this is in terms of head, in terms of meters. So we just need to get these into common units. So you could do it either way. You could either divide this equation by rho g to get this into head, or times this equation by rho g to get it into pascals. So I've chosen to do it that way. So said that the pressure rise due to the pump is equal to rho g times the head of the pump. So I'm going to times this equation by rho g, and if you do that and put it into your calculator, this is what you should end up with. So now I've got the pump characteristic curve in terms of pascals as well. And as I say, the operating point is where these two curves intersect. So these are the two equations I had on the previous slide. So the pipe characteristic curve and the pump characteristic curve. And if I equate them, now the only unknown is the volumetric flow rate. So we need to rearrange this and then solve for volumetric flow rate. So if you follow that through, you should end up with an answer of 0.087 meters cubed per second. So this is the answer that we've got. This is the volumetric flow rate. However, we just need to confirm that this answer is right, because we made an assumption in solving this. The assumption that we made was that the flow in the pipe was turbulent, and therefore we could use the friction factor that we were given. So we just need to check that that assumption is correct. Otherwise, this value we've got here isn't valid. So from the volumetric flow rate that we just calculated, or what we think it is, we can find the velocity in the pipe from the area. So that gives the velocity is 11.1 meters per second, and from that we can calculate the Reynolds number. So plugging that in and put in the fluid properties, we end up with a Reynolds number which is 1.11 million, and this is well over 3,000, which is the threshold for turbulent flow. So therefore the flow in the pipe is turbulent, and therefore our original assumption that the turbulent flow is correct, and therefore our answer is valid and therefore stands.